or is it okay?
I think it's okay.
Okay, cool. Thank you so much. All right, so folks, let's go ahead and we are gonna go back into our notebook, but we're gonna be looking at the 6.3 section, not the 6.2, right? So if you go on Canvas, you should be able to find a link for the 6.3 note. Again, it has some examples that have a lot of pictures, and then some where we're just going to be talking about setup. All right. So it's probably useful to have a copy of this because I think some of those pictures are really just kind of hard to draw by hand. All right. So let's get started. 6.3 is a section called Volumes of Revolution. So it's very similar to what we were doing with our disk and washer method, where we revolve something and it's going to give us circular cross sections, all right? But in this case, we're going to look at a different way of approaching problems, okay? Now, because this tends to be one of the last topics taught in Calc 1, I think a lot of students are like, oh, I don't want to learn another method. I'm only going to do disk and washer because that's just convenient and I've already learned how to use that. I would say, though, that it is very, very important, not just for your success on the final, but for your success in the future classes to think about knowing more than one method to do something, all right? Sometimes one method works, sometimes the other method works. And if you only know one, then you're not going to be able to solve all of the different problems, okay? But before we talk about the cylindrical shells method, what I thought we could start off with is just a little review of what we learned in chapter 6, okay? So we started chapter 6 by looking at the area between two curves. So this was section 6.1 in our textbook. And we took a look at two different situations. One where we could have things that were dx, and another one where we could have things that were dy. And so a classic dx picture might look something like this, where you have like one curve and you have another curve. You have a region in between them, and you can draw lines that have all the same top and bottom curve. And when you can do that, that means that you're going to find the area using this integral setup. So the integral from a to b, which are x values of the top curve minus the bottom curve, okay? And our a and b values, this would be an a value that's an x, and this is a b value, which is also an x value, okay? Now, if we were to think about how we could change this picture to make it more visually like, yes, I should use dy, what would you do to this picture?
Make the curve along the y-axis instead of x?
Yeah, I could go ahead and I could take this picture and I could sort of like turn it sideways, so to speak, right? And then I would have like a curve that was kind of like this, and then I'd have like another curve. And this time when I draw lines where one curve is always on one side, okay, then I have a situation where I have a right curve and a left curve. And so my right curve in this case is the blue one, And my left curve is the green one. And when I find my bounds, I better be using the y value of that bottom point and the y value of that top point, okay? All right. So after we learned about area between two curves, we went on and learned about volume by disk or washer method, and that was in section 6.2 in your textbook. And so we just saw a little bit of that this morning, but we could have situations where we have pi little r squared dx or pi big R squared minus little r squared. Okay, and so the reason why we sort of have two different versions is this one has no hole in the middle, whereas this one has a hole in the middle. Okay, and same thing when we thought about it dy, that the first case was when we had no hole in the middle, a solid shape. And then in this case, we had a situation that looked more like a traditional donut. All right. Now I do want to kind of put some pictures in here for like a classic case disk or washer method. And so what I might think is that if I am choosing to use disk or washer method, okay, and I'm choosing dx, what that means is that the lines that I draw had better be perpendicular to my axis of revolution. Okay, so let me draw like a classic picture of what these look like. So let's say that we wanted to do like a top curve and a bottom curve, all right, like we did in the other one. So let's say we have a big R squared and we have a little r squared. So the big R squared might be something like this, right? This would be the big R. And then our little r squared might be something like this. This would be our little r. Now, you could draw your reflection. So you'd have like this part and like this part. And let's say we marked off like from here to here. So from here to here, okay? Now, if I draw lines, like I'm saying, I want to do washer method, what I'm saying is that wherever my axis of revolution is, the lines that I draw had better be perpendicular to that. So I don't want to draw a line like that. That would not be a good line to draw if you wanted to use washer method. But what you could do is draw a line like this. That pink line is perpendicular to the axis of revolution. All of these pink lines are perpendicular to the axis of revolution, okay? So that's a pattern that we've seen, but we haven't actually made explicit. So I want us to write that down, that our slices, oh goodness, our slices are perpendicular to our axis of revolution. Okay. What that also means for some of us who are like, I still don't understand how she's making these decisions on whether I should use dx or dy, is that if you were rotating about the x-axis and you want to use washer method, it has to be dx. Okay, let me say that one more time. If you want to use, if you're revolving around the x-axis and you want to use washer method, it will be dx. Similarly, if I want to revolve around the y-axis, and I want to use washer method, then I'm going to have to use dy. Okay, so let's draw a picture that might help us out with that one. So let's say I have my axis of revolution right here. All right, we'll put a x-axis in there. But let's say I have my axis of revolution. All right, and I have, let's say, a right curve and a left curve. All right. Is this a situation of a hole or no hole? Like when I revolve that shape around the y-axis, will I have a hole or no hole?
Hole.
Yeah, you will have a hole, that's correct. And so if we even draw our reflection, we get something kind of like this. And any lines that we would draw would go this way. And all those pink lines are perpendicular to the axis of revolution. And those pink lines do not touch the yellow line. So that means I'm going to have a hole in the middle. Okay. But in this case, I can say the same thing, that the slices are perpendicular to the axis of revolution. All right. Okay, so we've got area between two curves, we've got volume by disk or washer method, and the takeaway for disk and washer method is that our slices need to be perpendicular to our axis of revolution. So knowing that, let's take a look at this case right here, okay? So it says, determine the volume of the solid obtained by rotating the region bounded by this graph and y equals 0 about the y-axis. So we've got a picture of the graph. I'm going to be revolving that around the y-axis, all right? And it's just going to be this green region right here. So what I'm going to do is I'm going to sketch my own picture, all right? And so I'm going to draw that, the y-axis here. This is my axis of revolution. And when I draw in the curve, I'll get something kind of like this. And this is 1 to 3, okay? 1, 0, 3, 0. All right, so if I want to use washer method, okay, and I'm drawing my reflection, we could draw the reflection like here. Yeah, and that would give me the shape. But if I want to use washer method or disk method, should my lines be parallel to the x-axis, or parallel to the y-axis, or perpendicular to the y-axis?
Perpendicular.
Perpendicular, right? We just said that slices are going to have to be perpendicular to that axis of revolution. Well, what's our problem with these pink lines right here?
They don't touch y equals 0.
They don't touch y equals 0. That's okay, because that just means there's a hole. But there's another problem here. Like if I look back up at my volume by disk or washer method, what was happening in my dy case is that I had a very clear left curve and a very clear right curve. But when I look at this picture right here that I've drawn, I don't have a left curve and right curve that are different. In fact, the left curve and the right curve are the same curve. Okay. And so in that case, we've said earlier, well, then we can't use this method. Okay. And I would say that yes, for this picture right here, we cannot use washer method. Okay. Any questions about why we can't use washer method? Okay. All right. So this is why we sometimes need a different method. All right. This method is called shell method. And a lot of times when we think about shell, we think about like seashells. That is not what they mean by shell method. Okay. So it's not a seashell. It's not a seashell. If you haven't seen the Marcel the Shell video, which is possible, if you haven't seen it, it's kind of funny. It's like short. It's like 4 minutes long. There's a link to it right there. So you can go ahead and watch that. But we're not thinking about shells in like a seashell situation. We're actually thinking about it more like the Russian nesting dolls, okay? So if you don't know what those are, it's like this picture right here with all the dogs. Like you see there's like the little pug dog and it's the smallest one. And then there's 5 dogs, but they're all different sizes. And each one of those fits inside of another one. Right, so this is the smallest dog. It goes inside of that dog. And then, what is that, a beagle or something? That dog goes inside the bulldog. And then the bulldog fits inside of the golden retriever. And then the golden retriever fits inside of the Saint Bernard. Okay? So that's what we mean when we're thinking shell method. We're thinking layers, kind of like an onion. All right? So this other picture, this middle one that I chose because it's easy to see, like the dogs are cute and everything, but I want us to focus on this one right here, the little pug with his head sticking out. But what I want us to focus on is those circles. And one might even say that those are concentric circles, circles that share the same center and they just kind of keep going out, all right? And then this one is maybe an even better picture of that, where I have like a circle here. Let's choose a different color, Judy. So I've got like a circle here, and then I've got like another circle here, and then I've got another circle here, okay? So what we're looking at now is not slices like slices of deli meat, but we're thinking about like a really skinny tube. And then around that tube is another really skinny tube. And then around that is a less skinny tube. And as you go out, the tubes get bigger and bigger in radius, okay? So when we say shell method, another name for that is sometimes people call it, that's not how you spell that, cylindrical shell. Okay. So cylindrical shells, another thing that you might want to visualize for a moment is, let's say that you get to the end of a toilet paper roll. You have the cardboard in the inside, right? And you have this cardboard on the inside, and it's kind of like that. That is what they mean when they say cylindrical shell. They literally mean like a roll of paper, okay? But what's special about these shells is these shells are infinitely thin. So cardboard is a little bit thicker than paper. If you took a piece of paper and you rolled it into a tube, that might give you a better image of what we mean by a cylindrical shell. Okay, And the reason why I wanted us to see these nesting dog things is because the shells sort of nest inside each other. So I have like one shell might be this blue one, but then the next shell out might be a little bit wider, but like the same height, okay? And maybe there's even another shell that's like a lot wider and a little bit taller, right? And if we slice it that way, it's another way for us to come up with the volume for a shape, okay? So let's take a look at some more professionally done photos rather than the ones that I'm trying to sketch in the corner of the notepad, okay? So if we scroll down, all right, we've got this function. Let's say we have f of x. Now this time, we're actually gonna be revolving around the y-axis, okay? So we're gonna take this function and we're gonna revolve it around the y-axis. What do you notice about the axis of revolution and this?
Parallel.
Yeah, they're parallel to each other, okay? So I'm gonna go back up here for a moment. We said that slices for disc and washer method are perpendicular to the axis of revolution. So if a problem says, solve this using disc and washer method, and you draw lines that are parallel to your axis of revolution, that diagram does not match or work, okay? So if you want to use washer method, you need to show me slices that are perpendicular to that axis of revolution. On the flip side, if you want to use shell method, then for shell method, your slices will be parallel to your axis of revolution, okay? And here's what the line that you draw represents. So this pink line here, that represents the height of a cylindrical shell. So it represents the height of the cylinder or the height of that toilet paper tube at that given place, okay? So let's see what this looks like when we actually revolve it. So if I take this shape and I revolve it around the y-axis, I'm gonna get a situation kind of like this, okay? And so this, even though the dogs was kind of like a funny intro to what a shell looks like, you can see that it follows that same idea where sort of you have skinnier tubes in the inside or skinnier shells, and as you go out, you are expanding, like each shell is a little bit bigger than the one before it, okay? And I think this line right here is the same line that we drew above, and that is easier to see now, I think, that it's the height of the shell, okay? So again, this would be the height of the outermost shell that you have. Where is the radius of this shell? Is the radius of this shell along the x-axis or the y-axis?
The y-axis or x-axis?
Tell me why you changed your answer.
Because it's hard to explain.
Okay. Well, if I just imagine the first shell, so if I'm looking at this left diagram, right, I know that the height goes up and down, so the height is along the y-axis, we could say. And the radius of the shell would be like, this is like the circle at the bottom. And so my radius is along the x-axis. Okay. And same thing if I take a look at the picture on the right, if I were to maybe dot in the circle that like goes back into the page, if I could draw in 3 dimensions, maybe it's a little easier for us to see that this represents the radius of the shell or the cylinder, and this represents the height of the cylinder. Okay, so let's summarize that a little bit. Let's say that if we are revolving around the y-axis, okay, so let's go back to this picture for a moment. If we revolve around the y-axis, that the height of the shell is the y value, and the radius of the shell is the x value. Okay. So the lines that we draw are the height of the shell, and we don't usually draw in the radius part. Okay, so we only draw the lines that are parallel, and those stand for the height of the shell. All right, let's take a look at this table right here. Okay, I know that it's difficult to make the decisions. I know it's difficult when one set of rules applies to one method and then the rules are totally different for another method. Okay. But that is, you know, depending on how far you're going to go in math, that is sort of what you're transitioning to, that not only do you have to know more than one method, you kind of have to know why you're choosing that method, okay? So I thought we'd put this into a nice little chart so we can refer back to. This might not be a bad thing to throw on your cheat sheet for the final exam, all right? But let's start off with our disc and washer method, because I think we feel a little bit more confident with that. So for our disc and washer method, okay, if I want to use dx for that, that means that my axis of revolution is the x-axis, and that the slices are either looking like this or like this. Okay, so we have an axis of revolution that is the x-axis, that the slices are either circles or circles with a hole in the middle, and these slices are perpendicular to the axis of revolution. Now, if I want to do disc and washer method, but I want to use dy, what does that imply about my axis of revolution?
It's going along the y-axis.
Yeah, it means that somewhere in the problem, it probably says revolve it around the y-axis. Good. Now our slices are still either going to be a circle or a circle with a hole in the middle. Okay. And same thing, our slices had better be perpendicular to the axis of revolution. Now, if I were you and thinking about my cheat sheet, I think this is a really good table to have on there. But what might be helpful for you is, I'm going to scroll back up for a moment, is maybe like these diagrams that we put here, to kind of include a diagram to go with your formula. So you're not just thinking, oh, like these are the rules, but you can actually see a visual of what it should look like as well. Okay. So that might be something that you add to that table, kind of like integrate more than one part of the notes into making the table more useful for you. Okay. So disk and washer method. If it's dx, it means it's around the x-axis. If it's dy, it means it's around the y-axis, okay? So let's see about our shell method. So for our shell method, okay, let's go back up to this single shell. So I don't know how many of you during this quarantine time have actually like gone through your pantry and been like, oh, I have this can of soup that's been back here for years. Maybe I'll just eat that for lunch today. Or look, I found this can of tuna fish back here in the cupboard, or this can of chickpeas, and maybe I should make some hummus. But if you think about any can that you see in a grocery store, the label part of the can, when you peel that label part off, what shape is that label? Yeah, the shape that you get is a rectangle, okay? So I'm gonna draw a shell, but a shell that has been sort of sliced and cut open so that we get a rectangle, okay? So this particular shell, if I unraveled it, would give me a rectangle, right? And this rectangle, this part is this part. So that is the height of my cylinder. But this part down here, what do we describe what I'm drawing as? Like, what part of a shape is that?
Circumference.
That's the circumference, good. And that part is this bottom part, okay? And the circumference of a circle is 2 pi r. So when I have these shells, I have like an infinite number of them. What I'm really saying is, listen, I have this soup can, I put one label on, and then I kept putting more labels on. And every single label that I put on makes the can wider and wider and wider. And so what we have in this picture is like a can that has a whole lot of labels on it. And every single label is so thin that we can say the area of that label is actually a rectangle because the thickness of it is so thin. So if I want the area of this rectangle, it's going to be 2 pi r h, right? I just take the length and I multiply it by the width. So I get 2 pi r times h. So when we think about our shell method, what we're adding up is all of these different cylinders. 2 pi RH. Now, I took the 2 pi and I moved it out to the front for the same reason I took the pi out, because it's a constant, all right? But there's nothing wrong with saying I want to keep the 2 pi on the inside. So you might even write this as the integral from a to b of 2 pi r h dx, okay? So the 2 pi r h comes from the area of each shell. But in the disk and washer method, the pi r squared comes from the area of the circle, Okay, so we're just slicing it in a different way. We have circles, and we know that area formula is pi r squared, so we better have a pi r squared in there. But with our shell method, we're doing 2 pi rh because that's the area of the slice we're looking at. We're looking at a rectangle, and I want to add up all the rectangles. So let's compare and contrast between the shell method and the disk and washer. So if I have dx at the end of a shell method, what I'm saying is my axis of revolution is actually the y-axis. And what I'm saying is my slices are shells that stand up this way. And what I'm saying is the slices are parallel to my axis of revolution. And for our cases only, okay, so for what we're going to cover in the scope of this class, the radius is going to be equal to x. All right, so if the letter at the end is x, then all you plug in for radius is just x. So take a moment and look at this last box in our little graphic organizer. How can you modify the statements that we've already written to write similar statements for shell method if I'm using dy? All right, take a moment and write those out, and then we'll kind of check those together. All right, who thinks they've got a modification for what our axis of revolution is?
Would it be the x-axis?
It would be the x-axis, yeah. Okay. That means that our slices are cylinders, but they're not standing up and down. They're kind of going this way. So they're going like along the x-axis, okay? Now, regardless, our slices will still be parallel to our axis of revolution. And again, this is only for our class. If we're only revolving around the x-axis, then whatever that last letter is, that's going to be our radius. Okay. So I know this is a lot to think about, Okay, it's a lot to kind of compare and contrast. And I want us to finish off today working through a few examples, okay? Now, when you study, though, I would really encourage you to think about like the reasoning behind all of these things and not just memorizing to execute them, but like, do you really understand how to make the decisions? Okay, does like the diagram make sense to you, and all of that? All right, so let's go ahead and go back to example number 1. So example number 1, we said, was like this: determine the volume of the solid obtained by rotating the region bounded by y equals x minus 1 times x minus 3 squared and y equals 0 about the y-axis. Okay, so we've seen this diagram before. We've got this polynomial, we have this little green region, and we're rotating it around the y-axis. And when we first looked at this problem, we tried using washer method. But we ran into a few problems. One of those problems was that the right curve and the left curve were exactly the same function. So I wasn't able to subtract them, okay? Another thing that makes washer method not the best method here is I would not need to know where the top of this little bump is, but I don't know where it is. Like I could kind of guess it's between 1.5 and 1, but I don't know an exact value, which means that I don't have a top bound if I wanted to set up washer method. So then we spent some time looking at like, okay, well, what is this other way that we could visualize? And so when we take this shape and we revolve it around the y-axis, we end up with, I know a lot of people have been making banana bread, but I don't know if anybody has a bundt cake pan. All right, but it's kind of also like, I feel like maybe Angel Food Cake, if you buy it from the grocery store, like already made, kind of has like a hole in the middle. Or like those Jello molds where it's like this shape, kind of like a hole in the middle, but then it's kind of like round on the outside. Okay, that's sort of what we're looking at right here. Now, since we tried washer method and this did not work, all right, now we're thinking, okay, well, what method could we use? And so when we take a look at this, all right, I'm going to add a little bit to this diagram. What we're seeing is this right here will give us one shell, okay? And then I could draw another shell, sort of like the inside one, where it was maybe like this. Okay. So I've got an inner function, I've got an outer function. I know there's a hole, but I'm going to look at it instead of inner and outer, I'm going to look at it as a bunch of cylinders nested inside of each other. Question for you, where is the tallest cylinder going to be? Like, what is the X value of the tallest cylinder?
Negative
Yeah.
2.
I would say about 2. So let's kind of draw that in. So if I go about at 2 and I draw a cylinder right there, yeah, that one looks like it's going to be the tallest out of all of them. Okay. What X values would give you the shortest cylinders?
1 and 3.
Yeah, 1 and 3. So if I erase this cylinder and I were to imagine a really short cylinder, at 1, the height would actually be 0. And if I thought about the one at 3, that height would also be 0, okay? So good job on identifying where the tallest cylinder will be and where the shortest cylinder will be, okay? So now that we've kind of done a lot of talking, that washer method is not going to work, so we need shell method. Let's go ahead and write out our formula and choose which one we want, okay? So I have 2 options when it comes to shell. I can say volume equals 2 pi the integral of RH dx, or I can say volume equals 2 pi the integral of RH dy. And the first one would have bounds of a and b, and the second one would have bounds of c and d. So which one of these options works for this case? dy or dx?
Dx.
Yeah, this is going to be dx, okay? Now, the one thing I haven't done is gone back to the original drawing and draw in the height of my shells. So the heights of the shells are going to be going this way. And that would show that they are perpendicular to my, or parallel to my axis of revolution, okay? So I've got one height there. I could draw another height, okay? All right, so let's see what we get. So volume equals 2 pi the integral of, if I have dx at the end, my bounds need to be x values, all right? So if we've chosen dx, then we better have x values as our bounds. So where is a good place to start counting these shells?
One to 3.
Yeah, we're going to start at 1 and we're going to end at 3. So 1 to 3. Now the radius is going this way. Okay, so I asked you earlier, where is the tallest shell and where is the shortest shell? But let's go back to this diagram for a moment. I'm wondering if you can tell me where the shell with the smallest radius is.
At the highest point.
No, it's actually not at the highest point. The skinniest shell is going to be right here, because this shell has a radius of 1. Does that make sense?
Yeah.
Okay. If I thought about the shell that you were talking about, which was at the highest point, okay, this shell has a radius of 2. And then what is the radius of the widest shell for this shape?
3?
It's going to be 3, yeah, because that is where our function sort of stops. So our biggest radius is 3. But check this out. Our radius is 1 at an x value of 1. Our radius is 2 when we have an x value of 2. Our radius is 3 when there's an x value of 3, okay? So earlier I said, well, just believe me, the radius is going to be the x value, but I think this diagram shows a little bit better why that's the case, okay? Because you start from the center and you're thinking, okay, how far out do I go sideways? That's going to be your radius, and that's also the x value. So when I go back to my equation, instead of r, I can go ahead and, that was supposed to be a 3. Instead of r, I can put x, because x represents the radius of the shell. Now the height of the shell is going to be those purple lines. And those purple lines are defined by my function. Y equals x minus 1 times x minus 3 squared. So instead of h, I can put x minus 1 times x minus 3 squared dx. Okay? So we have the 2 pi rh. This is our r. This whole thing here is our h. All right. So now that we've done the setup here, let's go ahead and simplify this so that we can find the integral, okay? So we're gonna go ahead and say it's equal to 2 pi from 1 to 3. And I'll give you a moment to FOIL out that height, and then you're also gonna multiply in that radius, okay? So take it step by step, but try and FOIL everything out so that you can get everything with just like powers, and then we can use our power rule. All right, so let me just pause here for a moment. Make sure that when we're foiling this out that we get the same polynomial that I have here. All right, any questions about this polynomial? Or are we good?
We're good.
Okay. All right, so let's take our integral. We're going to plug in 3 and we're going to plug in 1. So we definitely have to plug in both bounds because the bottom bound's not a 0. So we have to plug that in, the 1 in as well. All right, so we should end up with a final answer of 24 pi over 5. Okay. All right, so we're going to go ahead and start example 2, okay? So if you've looked ahead, you'll notice that example 2 and example 3 are going to ask us to solve the same question, but using 2 different methods, okay? So I'm going to scroll up to example number 2. All right, example number 2 says, determine the volume of the solid obtained by rotating the region bounded by f of x equals the cube root of x equals 8, and the y-axis about the x-axis, but I want you to use shell method, okay? So we've got our diagram here of our graph. We know that f of x equals the cube root of x, right? So that's this red curve right here. We know that one of the other boundaries is x equals 8, which is this line right here. And that my axis of revolution is the x-axis. So in this case, when I revolve the shape, I end up with this picture right here, okay? Now in this picture, is this a solid shape or does it have a hole in it?
It's solid.
Yeah, it's a solid, okay? So I can tell from the diagram, but I can also tell. So if I'm thinking about using shell method here, what directions do my lines need to go? Horizontal or vertical?
Horizontal.
Yeah, shell method, I've got a horizontal axis of revolution. So my heights of the cylinder should be parallel to that axis of revolution, okay? And you can tell in the second diagram here that like, well, maybe not that one, this one, this is the height of that shell. And that's the same as one of these lines that I drew above, okay? And so when we're thinking about the height of the shell, we need to think about our right curve minus our left curve. That will give us the height of the shell. But the radius is actually pretty straightforward. Our radius is just going to be the y value, okay? So if we were to go ahead and set up this integral, okay, I know if I have an x-axis of revolution that I'm going to need to use dy with shell method. So volume is going to equal 2 pi, the integral from c to d, rh dy. What are my C and D values going to be based off of the pictures that we have there?
Is it 0 and 2?
0 and 2, really good. I'm so glad that you didn't say -2 to 2. And if you were thinking that, I'm not shaming you by saying that, okay? But what I do want to point out is when you're finding your bounds, you should always use your original picture, okay? So not the reflection, but your original picture. What was the lowest y value here? Well, it was 0. And what was the highest y value? Well, that was 2. All right, so go back to your original to find your bounds, 0 to 2. Now, because my cylinders are sort of expanding out along the y-axis, my radius is just y. And to find the height of my shell, I need to do the right curve minus the left curve. So all that stuff that we learned in area actually comes back into play to be really helpful in setting up for washer and shell. So we've got this equal to 2 pi, the integral from 0 to 2 of y. Our right curve is just 8 minus our left curve is the cube root of x. Okay. But this right here is the mistake that not a single one of you have done yet. You might have thought about this, but then you've all remembered to rename the thing that is not like term. Meaning that we can't use cube root of x in here because everything else is a y. So we need the equation in terms of y to put in there. And when we do that, we should get not cube root of y or of x, but y cubed. Okay. Now from here, I think it's actually pretty straightforward to solve. It's probably a lot less work than the other problem we just did. I'm going to distribute my y. So I get 8y minus y to the fourth dy. And now I'm going to use my power rule. And I'm going to plug in 2, and I don't have to plug in 0 because I know that's just going to go to 0. All right. So questions on shell method.
Actually, I have a question about like in the beginning.
Mm-hmm.
So how did you change the cubed root, or like when you're doing the problem? Like, can you scroll down a little bit? Sorry. So how did you go from the cubed root of x to y cubed?
I took this equation and I solved for x instead of y.
Okay. Okay, perfect. Thank you.
Mm-hmm.
Okay, that makes more sense. Thank you.
Mm-hmm. All right. Any other questions?
I thought we were using the shell method because there was no right and left curves.
Okay. So you can use, so the reason why I wanted to do this example first is because you have to use shell method for that one. You don't have a choice. But there are oftentimes problems that you can do either way. You can do it using washer method, you can do it using shell method. But the setup for the two ways is different. So like the blue part right here, the shell method, that's really what I wanted us to practice. So just because you have, just because you can use washer doesn't mean you have to use washer. So the purpose of the second practice problem was just to reinforce, like, okay, how do we look at this and see cylinders rather than circles?
Okay.
Okay. Any other questions right now? I know that there are questions, and I know some of it is just like, I'm so confused right now that I don't know what my questions are. But if you have a specific question you'd like to ask before the end of class right now, that would be fine. Okay. Well, if there are no other questions right now, what I'd like us to do is to take a look at example 4, okay? And so this will serve as our exit ticket for today. I don't want you to solve it, okay? I want you to set it up, just like you did for last week's exit ticket where you set up the washer method, but you didn't solve it, okay? So same thing, I wanna see you set this one up using shell method. So making the decision, should it be dx or dy? What are my bounds? How do I know that? Okay. And once you've set it up, then go ahead and send me a picture. If you could email me by 12:30, that would be awesome. So I'll give you a moment to maybe take a picture of this if you need to, or screenshot it.
Can you go back to the other example?
Example 2?
Yes.
Is there anybody who still needs example 4? Okay.
Thank you.
You're welcome. All right, so folks, once you have example 4 written down or a picture taken care of, then you're welcome to take off. Just send me an email relatively soon with your setup for shell method, okay? And when we come back to class on Thursday, we'll spend a lot more time working on shell method practice, like visualizing it, seeing it, and then talking about cases where we have a lot of different choices and how do we know what choices we have, okay?
Sorry, can you scroll down one more time?
Of course.
Thank you.
Mm-hmm.